Hey all, so this is section 6.3 for Math 116, and this is future value of annuities. And 6.3, 6.4, we're going to see these things called annuities, and what's going to kind of be the distinguishing factor of these is that they have payments. So when we see payments, that means we're doing some version of annuities. We'll see we have a couple of flavors in each section. So for future values, that's the money that we're going to have sometime later. We're going to have two kinds. We're going to have ordinary annuities. That's for the payments made at the end of the period. And then a little bit later in the section, we'll have annuities due, and that's when the payment's made at the beginning of the period. In terms of our formulas, we have the N and the I that we saw in the previous section. So remember, N is going to be the total number of compounding periods. So it's the compounding periods times time. And I is going to be the interest rate per compounding period. So it's going to be the rate divided by the number of compounding periods per year. So those are going to show up in these formulas pretty much from here on out. And they're just to kind of keep the formula from getting quite as unruly with quite so many letters running around. And then the only other new thing here is this R, and that's now going to be the payment. Before we had future value and we had present value P. And so the R is going to kind of work in place of what would have been present value in the previous problems. Okay, so let's see what that looks like with some examples. Okay, so number one, find the future value of an annuity of $1,400 paid at the end of each year for 15 years if the interest rate earned is 5% compounded annually. And on these ones, they're almost all money, so we'll be rounding to the nearest cent. So let's kind of take this apart, and this is the spot where we kind of really start, we want to make that list just to keep ourselves organized because there's a lot of information in these. So we are finding the future value, and that is S. So S is what we're looking for, of the annuity of the $1,400 paid at the end of each year. So that's our payment. So that's going to be R is $1,400. End of each year. So that's the key that would tell you that this is an ordinary annuity because it's at the end of the period, not the beginning of the period. And this is for 15 years. So T is going to be time, and that is 15 years. If the interest earned is at a rate of 5%, so 5% is our R. Compounded annually, so that means M equals 1. And now we have kind of our list, so we know we're organized. And our formula, again, let me write that out here, and I won't do this every problem, but let me start at least with this first one. Okay, so there's our formula. So what we need is, our formula has S, R, I, and N going on. S is what we're looking for, so we're cool. We're set up for what we want to find. We know R. I and N, remember, are those calculated values. And so I equals R over M, and then that's where the list comes in handy. So R, 0.05. M in this case is 1, so I is just going to be the same thing as R. And the same thing with the next piece coming up. But for the next problems, that's going to matter because that will be a different value when M isn't 1. So then we need N, and N is MT, so compounding periods times time. So again, compounding periods is just 1, and so it will be the same as the time. But this will probably be the last example for a bit where it does that. So 0.05 and 15. And then pretty much we just plug everything into that formula and toss it in the calculator. So S is going to equal 1,400, 1 plus I, which was just the rate in this case, the N, which was just the time in this case, minus 1 over I, 0.05, and then close the bracket. So when I put this in the calculator, what I do is I kind of do it in little steps. So for one of these, I'll just kind of show my keystrokes on it. If you have, kind of a nice big graphing calculator where you can really see what you're typing, you can put that all in at once. In this case, though, like I said, I'm just using my little scientific one. So I will just kind of do inside to outside operations. So first thing I would do is turn it on and clear it, and then add these two together. So that's 1.05. That's going to be raised to the 15th. And then minus 1. And then rather than worry about parentheses and stuff, since this was all just kind of in a line, now I'll just hit equals, gets me a number, and I'll divide by this in the bottom. So divided by 0.05, and I'll just hit equals again, so that's this number, and then I'm just going to times 1400 and equals. And so then there's my answer. So S comes out 30209 point to 2.99. So if you're using a little calculator, I would suggest kind of doing it in a couple of stages, and then it's not that hard to type in. If you try typing the whole thing and you're trying to get all the parentheses in the right spot all at once, that's a lot harder to me. And then just to wrap up the problem, sorry I got wrapped up in the calculator. So S, this is our future value. So if we invested $1,400 at the end of each year for 15 years, this is how much it would be worth. And just to show, $1,400, and we're doing this for 15 years. So our out-of-pocket money would have been $21,000. And so this is just showing that you're getting interest that first year, which is then going to get, your interest gets interest. So this is how much money out of pocket, 21,000, and just over 30,000 is what we would have in 15 years with those sorts of payments. Okay, so number 2 goes, find the future value of an ordinary annuity of $200 paid quarterly for 2 years if the interest rate is 13% compounded quarterly. So let's start our list. We're finding the future value, so that's S again. So that's what we want to know. Our payments are the 200. Time is going to be for 2 years. Interest rate is 13%. Compounded quarterly. And the payments are also quarterly. And you'll see in this book those two things are going to match, which is important in the real world. But for us, they're always going to be the same. So quarterly. So that would be our M equals 4. And so there's sort of our basic list. And then let's get I and N. So N will equal M times T. So 4 times 2. So N is 8. And then I equals our rate, 0.13, divided by the number of compounding periods per year, which was 4. So that will be 0.0325. And then once we have kind of our list, we just shove it all in the formula and then shove it all in the calculator. So this is going to be S equals 200, that's our payment. And then it goes 1 plus I, so 0.0325. To the N, which is 8 minus 1, and then that's all over I, so that number again. And then toss that in the calculator, and I got 1,794.32 when I did it. The Weidmans want to save $35,000 in 2 years for a down payment on a house. If they make monthly deposits in the account paying 12% compounded monthly, what is the size of the payments? So what is the size of the payments that are required to meet their goal? So this one's a little bit different. This time we know how much money we want to have in the future. These guys want to have $35,000 2 years from now. So that's our future value. So this time we know S. And then if they make, and then T, I guess we know that is time, is 2. If they make monthly deposits, paying 12% compounded monthly, so both our rate is 12%, and then our M, our number of compounding periods per year, is 12, because it's monthly. What is the size of the payments? So this time we are looking for R. And let's go ahead and do our couple of calculated values. So N will be M times T, so that would be 12 times 2, or 24. And then I is going to be rate divided by number of compounding periods, so 0.12 divided by 12 would give us an I of 0.01. Again, just using those two formulas, and we're going to use these over and over and over, but these two formulas in that top box at the start of the notes. And we'll toss all that in and then solve for R this time. So S, we know the answer is 35,000, and what we want is the R. And then same old 1 plus I, so 0.01. to the n, which is 24 minus 1, all over 0.01. And so then all I did was toss all of that in the calculator. And honestly, when I was doing it, I probably didn't even write this step, but I got something like 26.97 dot dot dot. And I just went 35,000 divided by second function answer, and that copied this answer and divided. And that gave me R to 1297.57. So that would be the payments they have to make every month to save 35,000 in 2 years for that interest rate. And then just a note in terms of rounding in this section and kind of all these sections, which you've probably seen, but I'll just say it again. Use all the decimals you have. Even like if you think you're rounding reasonably well, it can still shift things enough in some of these formulas to then make you wrong in a little bit wrong in the answer in terms of the rounding, and then the computer marks you wrong. Okay, number 4. Patty Stacy deposits $2,800 in at the end of each of 5 years in an IRA. If she leaves the money that is accumulated in the IRA account for 25 additional years, how much is in her account at the end of the 30-year period? Assume an interest rate of 8% compounded annually. So she's gonna, the first part of this, we kind of have two separate problems going. From 0 to 5 years, this is going to be an annuity because she's making payments, these regular payments at the end of each year. And then after 5 years, she stops making the payments, so then it stops acting like an annuity. Now it's just a savings account. And so we'll use some of that math we learned back in 6.2 to figure out what happens after the additional 25 years. But right now we have to figure out how much money, first off, she has at the end of the 5 years that's going to be invested in that second step, the second 25 years. So for the annuity part of this, we'll do, her payments are $2,800. And let's see, we have a couple of different times going on. So for the annuity, that time is going to be 5 years. And she leaves the money an additional 25 years. So we're going to have this other T down here. It's going to be 25. How much is in her account 30 years? Assume interest rate 8%. So there's our R is 8% compounded annually. So that's nice. M is going to be 1. And so we can find, in that case, this is where the time and the interest just are the same thing because they're multiplied or divided by the 1. So we'll find the future value, and this is the future value. I'm going to go S5, say at 5 years. And we know that the payments are $2,800 a year, and it's going to be 1 plus the interest, because that's our I this time, raised to the time in this case, minus 1 divided by that I again, so 0.08. And so if we do that in the calculator, and what we get is S of 5 equals $16,426.48. So in 5 years, this is how much money she has. And so now what she's going to do is just let that money sit in the account for 25 years. She's not going to contribute any more, but this is like her principal or her present value. And now we're trying to find the future value, which was back in 6.2, 25 years later. So that would be at time would be 30 years. I'm just going to call that her future value 30 years later, which is what we're looking for. And this was P1 plus I to the N was the formula for that. And so our principal is this money that's in the account. So the 16,000. And then 1 plus I, so that would be 1 plus the rate stayed 8%. And then times the number of compounding periods. So the time's now 25. It's this one. M is still 1, so this is still 25. And then we throw all that in the calculator. So then in 30 years, she'd have 112,496 and 36 cents. Okay, B, suppose that Patty's husband delays starting an IRA for the first 10 years he works, but then makes $2,800 deposits at the end of each of the next 15 years. Interest rate still 8% compounded annually, so that's the same. And then he's going to let his money sit for 5 more years. How much will be in the end of the account? So the idea of this problem is to show that if you can put a little bit of money away early, that comes out better. So remember, she was making $2,800 payments for 5 years, and he is going to make $2,800 payments for 15 years. She let her money sit for 25. He didn't put any away for the first 10, and he's only letting it sit for 5. So this is to kind of compare and contrast in terms of savings and the better way to do it. So for this one, our R once again is the 2,800. T is going to be, we have a couple of T's. He's going to make payments for 15 years, and then he's going to let it sit for 5 years. Rate still 8%, and then M is still 1, and so I and N are just going to be these values again. So let's figure out how much money. The first 10 years doesn't count, so in 25 years, because 10 years of nothing and then 15 years of deposits, we'll figure out how much that is. So 2,800, and 1 plus same stuff as last time. But this time it's going to be 15 years, or 15 payments that he's going to make. So he's paying 3 times as much as she is, just to kind of put that in perspective. And that's 0.08. And so then we do that, and then in 25 years, so after he's been saving for 15, he's going to have $25.92. And now this is going to be his principal, how much he's going to put in the account. So then at 30 years, he's depositing this. And same terms, so 8% annual. But his is only going to sit for 5 years. And then if you toss that in a calculator, you get $111,707.02. So he put in 3 times as much money and came out with a little bit less money than she did, because she started her account early in life. So for all of you out there who are in your 20s, if you have any way you can start the IRA now, start the IRA now. Okay, so this is going to be the second flavor in this chapter, or this section, sorry. So still future value, that hasn't changed. But now it's going to be annuity due, or the payments are made at the beginning of the period. So either we're going to see annuity due in the directions, or something about the payments at the beginning, and that tells us that we're using this formula. It's fairly similar. It's a little bit different. Basically, it just accounts for the extra payment. And beyond that, all the definitions are exactly the same. So it's just if we see annuity due, we're doing this one. If we see ordinary annuity, it's basically the exact same thing, except just it's this little term right here is the only difference. So find the future value of an annuity due. So again, there's that kind of key, which formula we're going to need, of $300 paid at the beginning of each 6-month period for 9 years if the interest rate is 6% compounded semi-annually. So find the future value. So we're looking for S. And then R is our payment. That's $300. Beginning of each 6-month period for 9 years. So time is 9. Rate is 6%. And then compounded semi-annually, which is going to match that twice a year that we saw earlier in the problem. So then M is 2. And so then with that, we can do N, so that would be 2 times 9, which is 18. And then I is going to be 6% divided by 2, so that would be 3% for compounding period on the interest. And now we're just checking it in the formula, and we are looking for S. So we're looking for kind of what's the answer, not the R here. So we got 300. And then this goes 1 plus I, so 0.03 to the N, that's 18 minus 1 over I again. So all that's the same, and then it's just this same factor right here on the outside. So 1 plus 0.03. And then all that just goes into the calculator, and looks like S is 7235.06. So number 6 goes, what size payments? Okay, so what size payments? That means we are looking for R. Must be deposited at the beginning, so that means it's an annuity due, of each 6-month period, which kind of tells us it's about to be a 2 coming up, into an account that pays 7.2% compounded semi-annually. So little r, our rate is 0.072 compounded semi-annually, so that means m equals 2, so that the account will have a future value, that's our S, 160,000, at the end of 13 years, so that's our time. And then we'll find our I, so I would be rate over compounding periods, so that is 0.036, and our N would be time times compounding periods, and so that's 26. And they're just, again, tossing everything in the formula and letting the calculator do most of the work. So this time we know S, and it's R that we're solving for. So 1 plus, actually I'm just going to write that 1.036 to the 26 minus 1. Pretend like that's a decimal, over 0.036 and then 1.036 right there. And then all of this is just a number, so I threw all that in the calculator, and I got 43.40 with a bunch of numbers, and then just divided this by that one. And then R was 3686.53. So we'd have to make payments of just about $3,700 at the beginning of each 6-month period, twice a year, and then we'd have this much money in 13 years. Okay, and then these next few problems, they don't tell you which kind of annuity it is, ordinary or due. And so you have to kind of get that from the directions, and then what that will do is direct you to the right formula. So remember, ordinary annuities are going to be payments at the end. Annuities due are going to be payments at the beginning. And they have these two kind of slightly different formulas just with this piece. So we'll also be reading for that now. So for number 7, how much will have to be invested at the beginning? So beginning, when we see beginning, we know it's going to be an annuity due. So that's due. Each year, 12% compounded annually to pay off a debt of $50,000 in 6 years. So we are looking for the payment because we're looking for how much has to be invested at the beginning of each year. So that is a payment. So we're looking for R. And we know our rate is 12%, compounded annually, so always nice. M is 1. Pay off a debt of $50,000 in 6 years. So that pay off a debt, that's the future value, because we want to have 50 grand in 6 years or some balloon payment coming up. So I need that cash. So that is 50 grand, and T is 6. And in this case, again, I is just going to be the 0.12, and N will just be the 6 because of the M being 1. And from there, we're doing our kind of same thing, shove it in the formula. And then again, we just have to be careful because this one is beginning. Beginning means we're using this version of the formula. If it's an ordinary annuity, we're using that other one. So for this one, we're going to do, we know S is 50,000. And that's going to equal our payments, and then times 1 plus the rate, or 1 plus I. So that would be, in this case, 1.12 raised to N, which is 6, minus 1 over I, 0.12, and then times this same thing right here, 1.12. And then we chunk all that in the calculator. I ended up with 50,000 equals R, and then 9.089, divide that over, and my payments end up $5,501.15. Okay, so number 8, Mr. Gordon plans to invest $400 at the end of each month in an account that pays 9% compounded monthly. After how many months will the account be worth $40,000? So first part is state whether or not the problem relates to an ordinary annuity or annuity due. And so this one was at the end of the month, so that's going to be an ordinary annuity. And then we'll start our list. So R was the payments, and that's 400. 9%, so that's our little r. Compounded monthly, so that makes M12. After how many months will the account be worth 40,000? So that's a future value, because that's how much money we're going to have in the future. And let's see, so we need N. So N is going to be 12 times how many months, and that's the thing we don't know. That's the T. And this is going to be T in months, so that's a little bit different from what we're used to. So N is actually kind of an unknown. This is going to be like a 12T there. And then the last thing is I. So that would be our rate divided by our compounding periods. So that's going to be 0.0075. So when I set this up, we're going to have 40,000 on this side, payments of 400, and then this goes 1 plus this, so I'm just going to 1.0075. And then right now, I'm just going to let this be N. So I'm just solving for N, and then at the end, I'll kind of go back around to figure out what they actually want with this time and months thing. And then this is -1, and then over I again. So first thing I did was divide out this 400. And then that gave me 100 equals this stuff. And then next I multiplied both sides by this. Oops, I dropped a 0. So now that cancels out. And that makes this, the decimal moves 2 places, so that will be 0.75 equals 1.0075. And that's to the N -1. Now I'll add the 1 over, so 1.75 equals 1.0075 N. And then here is where we are solving for an exponent, so this goes back to the last chapter. We're going to log both sides, so we'll go log and log. Bring the N down front. 1.75 equals N times log of 1.0075. And then this is just a number, so all I'm going to do is divide both sides by that number. So here's what I'd be putting in the calculator. Log 1.0075. So again, that's right there. So that's what goes in the calculator. And then N would equal this value, and that equals, sorry, I'm kind of out of room here, 74.89 goes on, and I'm supposed to round up to the nearest month. So 74.89 blah, blah, blah means N is 75. So remember what N is. We're trying to find after how many months will the account be worth 40,000. It's 75 months, because N would have been the amount of time in years times 12. So that's exactly what we got, and so 75. Number 9. Okay, someone's grandparents are planning ahead. So grandparents plan to open an account on their grandchild's birthday and contribute each month until she goes to college. How much must they contribute at the beginning of each month? In an investment that pays 12% compounded monthly if they want a balance of $120,000 at the end of 18 years. So we're looking for how much must they contribute each month. So that is an R. Oops. R. Rate was 12%, and that's compounded monthly, so M is also 12. They want their future value to be 120,000. And this is be at the end of 18 years. So time is 18 years. And let's see, so we got that. So we need N would be compounding periods times time. So 12 times 18 would be 216. And then I is rate over compounding periods. So that would be 0.01. And now we're just solving. And again, it was an ordinary, beginning, sorry. It's an annuity due, my bad. So this would look like S equals, so S is the 120,000 equals R, that's what we're trying to work out. And then 1.01, that's raised to the 216 minus 1 over 0.01 times 1.01. So again, I just made all of this a number, and that should come out to 765.43. Some decimals, divide that over, and I got my R to be 156.77. So payments of $156 a month, and then they have $120,000 in 18 years for college.